Question 1 from the 2016 AP exam, has to do with lithium chloride. So this little image here, that was kind of distinctive, so I thought I'd throw that up there at the front. So here's the first part of the question. A student investigates the enthalpy of solution, delta H of solution, for two alkali metal halides, lithium chloride and sodium chloride. In addition to the salts, the student has access to a calorimeter, a balance with a precision of 0.1, and a thermometer with a precision of 0.1 degrees. To measure delta H for solution for lithium chloride, the student adds 100 grams of water initially at 15 degrees Celsius, to a calorimeter, and adds 10 grams of lithium chloride, stirring to dissolve. After the lithium chloride dissolves completely, the maximum temperature is reached by the solution, and that's 35.6 degrees. Calculate the magnitude of the heat absorbed, so it says magnitude of the heat absorbed by the solution during the dissolution process, assuming that the specific heat capacity of the solution is 4.18 joules per gram degree. Include units with your answer. Okay, so we're seeing what we're doing is we're going to heat up, we're going to dissolve some of this lithium chloride. And it says during the dissolution process. Well, dissolution process just means lithium chloride solid. Okay, you can put it in water and it turns into lithium ions aqueous and chloride ions aqueous. And that's all it is. So, dissolution just means dissolving. Notice that it does say the heat capacity of the solution, and that's going to be important because when we put our mass, we're not just the mass of the water, but the mass of the solution, so water and lithium chloride. So hopefully, you see it's a calorimeter, so we know that we're talking about Q equals MC delta T, and some people call that MCAT, because it looks like MCAT. And so the mass here, this is the mass of the solution. So we have 100 grams of water, and we have 10 grams of lithium chloride. So we have 110 grams of our solution. Okay, it says C, that's the heat capacity, that's 4.18 joules per gram degree. And we have change in temperature. Okay, change in temperature, it is final minus initial, so 35.6 degrees. Okay, and it started at 15.0 degrees. So going by significant figures, not significant figures, but by the place values, then we're going to see it's going to be 20.6 degrees as our temperature change. Okay, and when we do all this, grams are going to drop out, and degrees will drop out. We're left with joules, and the value that I get for this guy here is 9,470 joules. Okay, which we could also report if we want to as 9.47. Let me do that better. 9.47 kilojoules. So 940 is there. Okay, now we don't care about the sign of this because they said they want the magnitude of the heat absorbed by the solution. Okay, during the solution process. So it gets hotter because the heat is going into the liquid, into the solution. Okay, so we don't care about the sign of this. So that's 2 points. That's 1 point, 2 points so far. Okay, one if we just get the correct setup. And the next point we get for the correct answer with the units. If we did left off units, then you would lose that point. Okay, part B. Okay, explain why. I'm sorry. I forgot something. Okay, the second part of this here is determine the value of the delta H of solution for lithium chloride in kilojoules per mole of reaction. Okay, again, we're talking about the reaction is lithium chloride solid breaking up. So per mole of lithium chloride solid. And if you want to do a delta H, then what we want is we want Q, and we're going to divide that by the number of moles of whatever chemical was used to get that Q. So in this case here, we're talking about the kilojoules. So we want 9.47 kilojoules of energy, and we're going to divide by the moles of lithium chloride. Okay, so let's figure that out. We said we had 10 grams of lithium chloride. How many significant figures do we have? 10.0. Now we've got to take a lithium and a chlorine. We're going to add those together to get a molar mass. And when we do that, we get 42.39. And also, just as a quick warning, that when you're figuring out something like this, be sure and use the numbers on the periodic table given with the AP exam. Okay, so not just ones you've memorized. Go ahead and use those numbers to make sure you come up with the right value. And when we do that, we're going to get moles. We get 0.236 moles of lithium chloride. So back here to the first part, so the delta H of our solution then is going to be 9.47 kilojoules divided by 0.236 moles. And that's moles of lithium chloride. And officially what we're saying, because of our equation up here, for every mole of lithium chloride, we get 1 mole of reaction. So we can put that in if we want to. 1 mole of lithium chloride is 1 mole of reaction. Okay, so when we're done, then it's the same number. So that's the moles of reaction. Now the last little piece we need to do besides the answer here is look at the sign. If we're doing delta H's, we got to look at the sign. And we're talking about something that started at 15 degrees and went up to 35 degrees. Okay, so the delta H of this solution process, it is exothermic. Okay, so it is going to give off energy, so we're going to get a negative value here. So we could officially say that this is negative 9.47 kilojoules. Anyway, so my negative value, and if I put my numbers in, I'm going to get 40.1 kilojoules per mole of reaction. And that is my final answer. So back on the scoring guidelines, okay, we're going to get 1 point for here, okay, and you have to have the right sign for this to work, and you really should write in the units, but the units are right here, so if you left the units off and these just said negative 40.1, you'd actually be okay. That's dangerous. And then the other point is for getting those moles of lithium chloride. And so you don't necessarily have to show that, but if you got to this answer, then you obviously knew your 0.236. But if you didn't get that answer, or you lost the point for the negative sign and all that stuff, then we'd be looking for did you do this part? Did you change your 10 grams into moles? And that's worth 1 point. Okay, next part. To explain why the delta H solution for sodium chloride is different than lithium chloride, the student investigates factors that affect the delta H solution and finds that the ionic radius and the lattice energy, lattice enthalpy, which is the delta H associated with separation of a solid crystal into gaseous ions. So if you took sodium chloride and totally blew it apart into separate sodium ions and chloride ions, and gaseous means, they're totally separate from each other, the energy it takes for that, that's called the lattice energy. Okay, those contribute to the process. The student consults references and collects data in the table shown. So what has he found out? Found lithium ions and sodium ions. He found the size of those ions, their ionic radius. Because remember what we're talking about. We're talking about a little electron cloud. So the size of the electron cloud is the size of the ion. So write the complete electron configuration for sodium plus ion in the ground state. Well, personally, what I would do if I was doing sodium, I know I have 11 electrons. I'm going to draw what sodium looks like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now that's neutral sodium, and if I become sodium ion, I'm going to lose the outermost electrons, so those are gone. So what do I have left for my electron configuration is 1s2, 2s2, 2p6. Okay, that's my electron configuration for the sodium ion. Now, across the nation, people were making mistakes. They left that one in, just read more carefully there, the sodium ion. Okay, using principles of atomic structure, explain why sodium ion is larger than the lithium ion. Well, if we did the same thing for lithium, okay, we would say, okay, lithium has 3 electrons, 1s2, 2s1, okay, and that's the one that's going to be lost. So it would just be a 1s2 would be the ion there. So we can see what's happening is for sodium ion and lithium ion, okay, the electrons, the valence electrons, or you say the outer electrons, in sodium ion are in the 2s and 2p orbitals. Okay, the outer electrons in the lithium ion are in the 1s orbital. Okay, so we're talking about level 2, n equals 2 versus n equals 1. Okay, when the principal quantum number n increases, so 2 versus 1, okay, the average distance from the nucleus increases. Okay, and that's what we're looking for. So the principal quantum number, we're noticing that the sodium ions are coming from the level 2, n equals 2. Okay, for lithium ion, they're coming from level 1. And the farther you are from the nucleus, okay, the higher the value of n, the higher average distance from the nucleus. Now notice in this problem, it was not useful to come back and say, oh, but the ionic radius is, this size and that size, because that's given in the problem. So that's not useful stuff to say. And you don't really want to talk about, trends in the periodic table. You say, well, as you go down the periodic table, then, the size gets larger. That's true, but it doesn't explain anything. So you really need to come back to, what's different about these. They're in the same column, they're in the same family. But what's different is that, they have different principal quantum numbers, the 2s versus the 1s. And then as the principal quantum number value increases, then you get a larger distance, average distance from the nucleus. So that's the kind of stuff you want to go for. Okay, which salt, lithium chloride or sodium chloride, has the greatest lattice energy? Well, hopefully you learned about lattice energy when you're talking about ionic compounds, and it all has to do with charge and distance, because we're really talking about Coulomb's law, so Q1, Q2 over D squared. Okay, that whole thing, so the attraction. But what's happening here is lithium and chlorine and sodium and chlorine, okay, this is a +1 ion, and chloride obviously is both -1 ions. So it's not the charge that makes a difference, okay, because it's the same charge. It has to be the distance. So which salt has the greater lattice energy? Whichever one has the smaller value of D is going to have a larger attraction between the particles. The bigger, if you have a big ion like this, okay, then the distance here between the two ions, so here's a plus ion and a minus ion, that distance, if it's a large distance, then that's not a very strong attraction. But if you have a small distance between two ions, okay, then the small distance is going to be a lot larger. If the denominator of your Coulomb's law is a small number, then your answer here, your attraction is going to be larger. Anyway, so what you want to say is that lithium, okay, is smaller, has a smaller radius. Than sodium. And that's not enough of an answer because, again, we just had on the chart over there, it said lithium is smaller than sodium. Okay, why does that make a difference? Okay, because by Coulombic attraction, therefore, the Coulombic attraction between sodium and chlorine, lithium and chlorine, chloride, is greater than the sodium and the chloride. Okay, so because it has a smaller radius, that's an important piece, but why does that make a difference? Okay, why it makes a difference is because of Coulomb's law. The Coulombic attraction between that smaller ion is going to make the attraction greater. Okay, letter E. Below, this is that picture we saw, shows a lithium chloride crystal. Well, when chlorides become ions, chlorine becomes ions, they get bigger. When lithium loses electrons, they get smaller. So the big one over here, like this guy here, that's going to be the chloride ion. And the little one over here, that's going to be a lithium ion. So the point is just filling those two things in. And there were people, when they filled them in, they just put chlorine and lithium, not the ions, and they didn't get point for that. So again, those are ions. This is an ionic compound. Those are ions. So you had to put the charges in. Okay. Okay, part F. The lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break the ions apart. So the lattice energy is a positive number because it takes energy to pull all these positives and negatives away from each other. But when you dissolve them, the dissolution of lithium chloride is exothermic. So we saw that it heated up when we dissolved it in water, so it's exothermic. So the question is, what is the particle-particle interaction that causes things to be exothermic? Okay, so there's a lot of stuff going on. You got to put energy in to break the ions apart. You got to put energy in to separate the water molecules from each other, and then you're going to put the water molecules around the ions, and that's the important piece right here. So we can see here's these positive purple ions. Water molecules have a negative N. They're polar. Okay, and the water molecules here, they're showing that the red is negative and the whites are positive, and it's not exactly right. They're not supposed to be showing that it's not ionic. Okay, you don't want to make that kind of bad. But the idea is that one end of it's a little bit negative and one end of it's a little bit positive. We say it's somewhat negative, partial positive, partial negative charge. But same idea. It's a pretty picture. So what happens is that the negative ends are attracted to the positive ions, and the positive ends of the waters are attracted to the negative ions. Okay, and we have a name for that, and that is called ion-dipole interactions. Okay, the ion is the ion, and the dipole is the water. So ion-dipole interactions. And the question says, for each interaction, include the particles that interact and the specific type of intermolecular forces. So we just did the second part, the ion-dipole interaction. And the other part we want to do is who is involved? The lithium ion and water. Okay, that's one group. And the chloride ion and water. Okay, those are the particles that are involved, and this is the name of the interaction, ion-dipole interaction. And we don't care about other interactions because they're all ones that take energy in. These are the ones that lead it to being exothermic. And that is the question. Now let's go back over real quick and just say where were the points awarded for this question. Okay, so first thing here, when you got to the first part here, we got 2 points here, one for getting to the right answer, okay, and one for the correct setup. So we'd see that there. So that's plus 2 points for that first part. Okay, second part is you got to figure out the delta H of this. So 1 point was just for getting to these number of moles. You didn't have to show that specifically, but then the second part was for getting to the right answer with the sign. So it had to have a negative sign on there to get that point. So there's 4 points so far. Okay, for part C, using the principles, okay, explain why sodium ion is larger than lithium ion. Again, I think I skipped a part. Okay. We got those 4. Oops, okay, I didn't go down. Okay, so back here, we had to figure out the electron configuration for sodium ions, so just writing that was worth a point. And then we had to go back to this part here, explain why, and this is worth 1 point. So we had to notice that the electrons were coming from a higher value of n, higher principal quantum number, and that why does that make a difference? As the principal quantum number increases, then you get farther from the nucleus. Okay, so last part here, so part D, which has the greater lattice energy? Okay, so greater lattice energy has to do with the size and charge. Okay, the charges are all the same, so it's just size. So it has a smaller radius, okay, which is an important thing to say, but that was given in the problem. So here's where the point comes. The point comes from saying that that smaller radius gives you a greater Coulombic attraction between lithium and chloride. Okay, and then for part E, okay, we get a point for writing lithium ions and chloride ions there. And then the last 2 points were for the talking about being exothermic. Okay, 1 point here was for noting what particles are involved. So we're talking about lithium ions in water and chloride ions in water. So that was 1 point's worth. And then saying that that was called the ion-dipole interaction. Now, it turns out I didn't actually have to use those words as long as you describe the fact that the polar water molecule, the negative end would be attracted to the positive ion, and the positive ion would be attracted to the positive end attracted to the negative ion. That would get you the point if you described it nicely. And that's the 10 points for this first FRQ.